insists that I am in New York. No, in Salt Lake City, in Denver. Whatever. Anyway, back to where we were. I explained the difference and the intersection, which can always be replaced by complementation and union. And so obviously if you want to do S minus T, you take S intersection T complement, which of course then is equal to S intersection union T, and the whole thing complemented. You just plug this in for that, and that'll give you that. Are there any other questions? No other questions? All right, so we have at this point dealt with the elimination of several things. First, useless symbols. Second, epsilon productions. And third, unit productions. Now, that then was the basis for Chomsky normal form. C and F, where productions are of the form variable goes to two variables or a single terminal. And now we're dealing with Greibach normal form. This should be an H. G and F, where a production goes, every production starts with a terminal and then has 0 or more variables following. We've already done Chomsky normal form, and now we have to do Greibach normal form. Now, in order to do Greibach normal form, we first have to eliminate left recursion. Left recursion is the situation where you have a variable, and in one or more derivation steps you get something that starts with that same variable. Now, there are two aspects to left recursion. There is immediate left recursion, and there's general left recursion. Immediate left recursion is if you have a production where the right-hand side starts with that variable. So this is a single production. To see that this is a different story for general left recursion, consider the following. A goes to B, A, and B goes to C, B, and C goes to D, C, and D goes to A, D. So in that case, there is no immediate left recursion. None of the productions start with the right, where the right-hand side doesn't start with the variable. But obviously, you can go from A to B and then to CBA, and then from there to DCBA, and finally to ADCBA. And so here is that general lift recursion, even though this grammar, and of course you need other productions, but I'm just writing down the ones that are relevant. In this case, you obviously have a situation that shows that a variable, in this case A, would generate a string that starts again with that variable A, but there is no immediate lift recursion anywhere. Okay? So the first thing we're going to do is we eliminate immediate lift recursion. Elimination of immediate lift recursion. And that means we now are looking at all the A productions. So we have a bunch of A productions, and we write down all of them, and we group them together in two groups. A productions that start with A, and A productions that do not start with A. Beta I does not start with A. Okay? So these are all the A productions. And now we replace them by, well, A goes to beta 1 through beta n, or beta 1A prime through beta n A prime. And A prime then generates alpha 1 through alpha m, or alpha 1A prime through alpha m A prime. And the claim is that when we replace these A productions by those A productions, we get exactly the same thing. Well, let's look at what the original A productions produce. Okay, we basically get, as long as we use the A productions that start with A, we get alphas. We get a bunch of alphas, as many times as we want to derive from A to another A at the beginning. So we can get any of the alphas. And then eventually we will have to use a beta. So if we look at the set of all strings that we can possibly get from the A, then this is a beta, because the beta obviously has to start that string. So one of those betas, or any of the alphas, and as many of the alphas as we want, so this is star. So this is what we really get from this set of productions. Okay? Any one of those betas is a possibility, and then any sequence of alphas in any order, because obviously as long as we use this, we are going to get any alpha which we want. Now if we look at this, the A prime, what does the A prime generate? The A prime generates alpha 1 through alpha m. If we use this, or any number of alpha 1 through alpha m. So that's what we get from the A prime. And now what do we get from the A? Well, we either get beta, or we get beta followed by whatever we have from A prime. And so that beta, if we use any of these productions, then we get just the beta, one of those betas. On the other hand, if we use one of those productions, we get any beta followed by whatever alpha A prime generates, which is one or more alphas. So what that means is either we get betas followed by no alpha, or we get betas followed by one or more alpha, which is of course exactly betas followed by zero or more alphas. And so by replacing these A productions by those A productions, and of course we need the A prime as well, we are going to get an equivalent set of productions. And that equivalent set of productions obviously has no immediate left recursion. Because by definition, the betas do not start with A, and the A prime obviously aren't present in the alphas, so they can't be in the alphas. And because we assume that we apply this construction only after we've eliminated all useless symbols, all epsilon productions, and all unit productions, it follows that none of these alphas are epsilon, and that means that the alphas are actually stuff that is something, not epsilon, and therefore the alpha obviously by definition won't contain any A prime, because the A prime was just introduced as a new variable, and therefore neither the A productions nor the A prime productions have immediate left recursion. So when we replace this set of productions by that set of productions, we generate exactly the same symbols, the same strings, but now we do that without having immediate left recursion present in those productions. So that eliminates immediate left recursion, and now we can try to get rid of general left recursion. And so what we do is we start by fixing an order.
Professor,
A1.
before we continue, I have a question.
Yes.
So, can we go to the previous slide for a second?
You have to talk louder. I don't hear you.
Is it possible we can go to the previous slide?
I am already at the previous slide.
Sorry. Okay, so just to make sure that I understand what's going on here. Right here we had a left recursion aspect where we had a string.
No, we had an immediate left recursion.
Immediate left recursion, so that is a big difference there. Okay, so then between each one of them had an immediate left recursion. So what?
Well, not each one. We have, this is the group of those where there is immediate left recursion, and this is the group where there is no immediate left recursion because the beta i's do not start with that variable A.
Okay, so then we split those two up into A prime and A minus 1. Is that correct? And then from there...
Where is A minus 1?
I'm sorry, right below that first line.
This is A and this is A prime. A generates, we basically keep all the A goes to beta 1 through beta n. This is the same thing as that. And then we replace these by beta 1 A prime through beta n A prime. And then we add A prime productions, which produce A alpha 1 through alpha m, this with the A stripped off and that with the A stripped off, so alpha 1 through alpha m, followed by alpha 1 a prime, etc. through alpha m a prime.
All right, this is where I'm losing myself, because a prime is actually the combination of alpha.
No, a prime
1.
is a variable.
Okay, so we made
A prime is a variable that generates stuff. So the right-hand sides of the A prime productions are the alphas, as well as the alphas followed by A prime.
And we're going to substitute, we're going to put that in the previous A, where
We're going to replace the previous A productions by this set of A productions and the A prime productions.
I see. So now we don't have any A's, we only have A primes and...
No, we have A's. There they are.
So we're adding this new A prime, and now that we're adding the new A prime, what happens over here at the right side? Do they cancel each other out?
Nothing cancels out. All that is that the A's now still generate exactly what the A's before did. What does this variable A generated is exactly what this variable A generates, except we do it differently. And we do it in such a way that there's no immediate left recursion.
So by putting in the A prime, we actually are able to get rid of the left recursion on A.
We don't have any left recursion. The A's don't have any left recursion because by definition none of the betas start with A, and the A primes don't occur on the right hand side because the alphas will have no A prime because A prime didn't exist when we defined the alphas.
Okay, I think I am understanding what's going on. And what's this last part up here on the right side where we have B1 all the way to Bn, and then the same thing times out?
This is what these productions generate. And then we verified that the new A productions generate exactly the same thing.
And they do?
Yeah.
Okay. Thank you.
Okay. All right, so now we have to get rid of general left recursion. Well, what we do is we fix an order, and interestingly enough, any order will work. You just have to fix an order among the among the variables of your grammar. So these are now the variables of your grammar, and now that order is fixed, and you have to stick to it. And so now we have the following little algorithm. I from 1 to n minus 1 do for j from 1 to I minus 1 do. So what so what we are going to do, well, before I write the algorithm down, let me tell you where we're going here. What I want to do is, this is the goal. We're going to change the productions in such a way that whatever an AI production has on the right-hand side cannot start with anything that is I or I minus 1 or anything above. So that means that AI in general, if it produces a T alpha, then T has to be greater than I, strictly greater than I. So that means that if I have an AI production, then it could have an AI plus 1 or an AI plus 2 or whatever, but it can't have anything above. So, in other words, if I start with the A1 productions, well, it could start with A2 or A3 or A4, but it cannot start with A1. If I then look at the A2 productions, the A2 productions can only generate something that starts with A3 or A4 or whatever, but not with A1 nor with A2, and so on and so forth. So basically, whatever is at the beginning of any of these productions, now of course it could be a terminal. Terminals are safe, but if it is a variable, then the variable has to be further down. This is where the fixed order is important. The variable that is up here has to be further down. All of these have to be further down. And that, of course, means that an AN production must start with a terminal, because there is nothing underneath following the AN. The AN is the last variable. So that means that if we have an AN production, that production has to start with a terminal. Can't start with a variable, because all the variables that are available are n or n minus 1 or whatever, none of which are permissible according to this. So that means we are now doing the following. For I from 1 to n, for j from 1 to I minus 1, do replace any production AI goes to HA alpha. That's, of course, a taboo production, because J goes from 1 to I minus 1, so J in particular is smaller than I. And so if we have AI goes to HA, then that is a taboo production according to this, because that's what we're shooting for. So any production of this form is replaced by AI goes to gamma 1 alpha through gamma S alpha, where HA goes to gamma 1 through gamma S are all HA productions. At this point in the algorithm. Now, it is crucial that you actually do the two nested for loops exactly in the order in which it is written down. So you take, for a specific I, you take first j is equal to 1, and you troll for AI goes to A1. If there is, then you replace. Now, as you will see, because of the way in which this process is carried out, the HA productions, which of course are before the AI, will already satisfy this requirement. So that means that the HAs do not start with anything that is A1 through HA. They can at best start with HA plus 1 or HA plus 2 or whatever. And so that means that now we're basically pressing this whole thing one step further down. And so when we carry this all out, then at the end of that for loop, the Che loop, we now have a situation where at worst we have AI goes to AI followed by something. And so this is immediate left recursion. Eliminate immediate left recursion. Among the AI productions. And that's the end of that. This is the whole algorithm. So let's look at an example. Say we have A1, A2, and A3. We fix this. And so A1 goes to A2, little a. A2 goes to A3, little b. And A3 goes to A1, little c, or d. Okay. So if we look at this algorithm, we go for I is equal to 1. And there is, of course, nothing for Che. So in this algorithm, Che goes from 1 to I minus 1, which means for I is equal to 1, this is empty. There is nothing, no case in the Che loop. And so the only thing that could happen is that we have an immediate left recursion. Well, we don't have any immediate left recursion. A1 goes to A2, so this is fine. Then we take I is equal to 2. That's the next case. And in this case, we are having a value for Che. Che is equal to 1. So we're looking for A2 goes to A1, followed by something. Well, there is nothing of that nature. And so we're done with the Che loop. Now, so we've done that Che loop. There is only one case, Che is equal to 1. And then we look for the immediate left recursion. Well, there is no immediate left recursion either. A2 goes to A3. It doesn't go to A2, and therefore there's no immediate left recursion to be eliminated either. So we proceed to I is equal to 3. And so the first case is Che is equal to 1. And yes, there is an A3 goes to A1. So this is exactly what we're trolling for in that Che loop. Replace any production AI goes to HA alpha. In this case, A3 goes to A1 C. And we replace that by what? We replace it by the A1 goes to whatever A1 produces, which is A2A in this case. So we get A3 goes to, so we take this A1 and replace the A1 by A2A. And then we have, of course, the little c. And so that is now the what we get from the A3 goes to A1 production, and of course we still have D.
Professor,
So we get rid of this, replace that.
sir,
Yes?
I'm so sorry. Could you tell me why J didn't move to 2 if J equals I minus 1
Because
when
we're not there.
I equals 3
I is equal to 3. Correct.
and J stays at 1? It's not actually J equals I minus 1.
It's a Che loop. Look.
I see. Yeah.
Che from 1 to I minus 1.
Yeah. Oh, thank you. Sorry, I needed to see it again. It's so much faster.
Okay?
Yes, thank you.
I mean, I do assume you know what a for loop is. So we get the first
Yes.
value of Che,
It's
which is
the
1.
back and forth between the tiles that's challenging. I apologize. I do know what a for loop is.
Okay, so we have Che is equal to 1, and we replace the A1 by whatever we get from A1, which in this case happens to be just a single production. So we replace the A1 by A2 little a. And of course that gives us the C. And then we have the A3 goes to D. And so that is the situation for Che is equal to 2. And now, of course, we proceed to Che is equal to 1. And now we proceed to Che is equal to 2. Because as it happens, yeah, we didn't have any A3 goes to A2 originally, but in the process now we do have an A3 goes to A2, which is of course exactly what we're trolling when we have I is equal to 3 and Che is equal to 2, so there's an A3 goes to A2. And so what that means is now we have to replace this A2 by whatever A2 produces on the right-hand side, which is A3B. So we get A3 goes to A3B, followed by little a and little c, and we have D. So we get rid of these two productions and we replace them by those two. So that gets us to the end of the Che loop. Che's 1, we did that here, and then Che is equal to 2, which is I minus 1. So this is the upper bound, I being 3, so I minus 1 is 2, and so this is Che is 2. And now we have to see, is there any immediate left recursion? Well, there wasn't initially, but now there is, because we have A3 goes to A3. And so what we do then is we get A3 goes to D, or D A3 prime. Now we just apply this process for the elimination of immediate left recursion. We have one alpha and we have one beta. So in this case we have, this is our beta, it doesn't start with A3, and the alpha is BAC, because this is A3 followed by that alpha, so this is our alpha, BAC, and so we have beta, which is the D, or beta followed by A3 prime. And now we have to write down what the productions for A3 prime are. Well, this is alpha, which is BAC, or alpha followed by A3 prime. So that is then A3 prime goes to BAC or BAC A3 prime. And so what we have then is we have now achieved the goal, which was that if we have a production, AI goes to AT something, alpha, then that AT has to be further down in that list of variables. The index T has to be strictly greater than the I we have here. And that, of course, is true because we have A1 goes to A2, A2 goes to A3, and the A3 doesn't go to any variable at the beginning, only terminal. So if we take this, then we have this set of productions plus this set of productions, which then achieves the goal of eliminating left recursion, generally. Because obviously, if that is the case, if we have this property that if there is a variable and it generates another variable, that variable has to be strictly further down in that list, then of course that means there is no way of getting left recursion, because left recursion basically requires you to go back up again. And since that can't be, you have now eliminated left recursion in general. And now actually we have done most of the heavy lifting already to get Greiberg normal form. Because what we really need in order to get Greiberg normal form is to make sure that everything starts with a terminal. Well, we know already for the A3s in this case that they all start with a terminal. And so what we can then do is we take those A3 productions and plug them into the A2 and A1 productions if need be. So there's A2 goes to A3b, which means we're going to have A2 goes to A3, well that's D followed by B, or D A3 prime followed by B. So now we have our A2 productions by substituting the A3 productions, which necessarily have to start with a terminal because this is the last variable in that list, 1, 2, 3. It follows then that all these productions have to start with a terminal, and if we then substitute the A3, which we did here, for the A3 right-hand side, for the A3 occurrences, in this case the A2 production, then again we're going to get A2 productions that start with a terminal, and then we can take the A1 production and do the same thing with the A2. So we have D, B, A, or D, A3 prime, B, A. And so what we have then is the A1 productions start all with a terminal, the A2 productions start all with a terminal, and the A3 productions start all with a terminal. And so the only thing that needs to be done in order to clean the whole thing up is to get rid of these spurious B's and A's that are terminals that really have to be replaced by variables, using the same trick that we've used before. And so what we're going to get is then A1 as final answer is D XB XA, or D A3 prime XB XA. Then A2 goes to D XB, or D A3 prime XB. And then A3 goes to D, or D A3 prime. And then finally A3 prime goes to B XA XC, or B XA XC A3 prime. And the only thing that is missing are xa goes to A, xb goes to B, and xc goes to C. And with that, now we have the final answer of getting Greibach normal form for this original question, for these original grammar productions. Okay. Any questions about this?
Yes, I do. I somehow got lost in between A1, goes to DBA, all the way to A1 equals DX, but
You have to
DXD.
speak up. I don't hear you.
Okay, sorry about that. Can you hear me now?
Yeah, but you have to speak up more because if I don't hear you, your colleagues don't hear you either.
Sorry about that. Are you able to hear me now, Professor?
Yes, now this is much better.
Okay, so I somehow got lost in the part where we went from um, A1 is DBA, and then at the actual answer, A1 is DXBXA. Where do we input those two X's, and how do we get there? I wanted to wait
Oh,
until you were.
look, remember what we are shooting for. We want every production to start with a terminal and then followed only variables, 0 or more. So what we have here is the A1 is little d, little b, little a. So that production isn't quite correct because yes, it starts with a terminal, but then it needs a variable here and it needs a variable here. Well, that's the same trick that we've used for Chomsky normal form. If we have a terminal that we don't really want to have, we replace it by a variable. So the b is replaced by xb, which is a variable, and that variable then generates just b. So this is just formal fun and games, but there's nothing very deep. And the same thing for the little a. xa goes to a, so we have d xb xa. Okay?
Yes, I think I understand.
And then the same thing for this. So there's the d, which is what we need, and then we have a variable a3 prime, and then we have to get rid of that terminal b and the terminal a the usual way, xb and xa, and so that's the same deal. And then a2, there's first production, we have to do that xb, and the second production we have to do the xb as well for the b here. And then the a3 is okay, but the a3 prime we have to do the same trick again. Any other questions? So what you can see here is, of course, that it is crucial that you stick to the order and you do strictly j is equal to 1 and then j is equal to 2 and so on until you get to j is equal to I minus 1. Because if you do not do that in the correct order, going 1, 2, 3, and so on, then you would easily see how this would go wrong, because you have A3 goes to A1, and so that gets then to A3 goes to A2, and that then gets to A3 goes to A3. And then you have to eliminate the immediate left recursion, which of course we know how to do. There it is. Okay, any questions?
Yeah, I have a question on this slide. How come on A3 prime when it goes to B, XA, and XC? How come it doesn't go to XB, XA, and XC?
That's very simple, because you are supposed to start with a terminal. All productions,
Oh, okay. I see.
all productions have to start with a terminal, and then there are 0 or more variables following. Now, that's fine. Yeah, this is a. You may think this is sort of a silly question, but it is important to see why we're not doing it for the B, because that is the terminal that starts at the beginning of each. And so if you look at all those productions, every one of those productions starts with a terminal and then has variables following. 0 in this case, 1, 2, 3.
So did we get rid of all the recursions by putting A prime?
No. We don't ever get rid of all the recursions. We get rid of the immediate left recursion, or the left recursion in general. If you want to get rid of all the recursion, you will end up with a finite language, which is not particularly useful, because you don't want to be told that your program is no good because it is too long.
Oh, I see. So in that case, this is so that we can actually do more complex sentencing in a non-finite language?
Right. Basically, if you have left recursion, if you have this type, where are we? Here. If you have this, A goes to A alpha, then basically when you do the parsing, you basically expand variables. And so this kind of thing is kind of evil, because it means you're going to expand the variable A into something that starts with that variable A again, and then you would expand this variable A again into this, and so the whole thing would never end. So what you would basically end up with is you get A, and then you get A alpha, 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 and you can see that that is never going to end. You don't want that. You don't want your compiler to run into this kind of loop, because it would mean that your program would never be parsable. So, but it is important to understand that it is left recursion that is evil. It's not recursion. If you try to get rid of all the recursion, then basically you're going to make this whole thing useless, because you do need recursion in order to be able to get anything reasonable. Okay, any questions? Let's look at another example, perhaps. Say we have A1 goes to A1, A1, or A2, A2, and A2 goes to A3, A3, and A3 goes to A1, A1, or little a. So in this case, we start with I is equal to 1. There is no J case, so no J. But there is immediate left recursion. So we have A1 goes to A1, A1, or A2, A2. So this would be our beta. This would be our alpha. Okay. And so we have A1 goes to A2, A2, or A2, A2, A1 prime. And A1 prime then goes to A1 or A1, A1 prime. Now, this A1 looks kind of suspicious, but it does not introduce any left recursion, because the A1 prime goes to A1, but that doesn't really generate any left recursion. Okay, so now we have I is equal to 1, then we go I is equal to 2, so j is equal to 1. We're looking for A2 goes to A3. I'm sorry, A2 goes to A1. This is A2 goes to A3, so there is nothing. And there's no immediate left recursion either, so we're done. Then we go to I is equal to 3. Well, we have j is equal to 1, so we're looking for A3 goes to A1. And there is, we have A3 goes to A1, A1. So we're going to replace the A3 by this A1 is going to be replaced by whatever we have. So this is A2, A2, or A2, A2, A1 prime, or I'm sorry, we're going to replace the A1, this A1, by A1, A2, A2, and then this of course followed by A1. And then we have the A2, A2, A1 prime, followed by this A1. And then we have the little a. So we're basically replacing this by that. No, we're not replacing. Sorry. We keep this is fixed. Okay, we're replacing this A3. That's what we're replacing. So this is fixed for the moment. The A2 is fixed, and then the A3 is I is equal to 3, j is equal to 1, so we replace the A1 by whatever we had for the A1 productions, which is A2, A2, this followed by the A1, and the A2, A2, A1 prime followed by the A1, and then of course we have the little a. So this is j is equal to 1. Then we have j is equal to 2, and yes, we have the A2 here and here. So there are two cases where we have to substitute the A2 for the A2, the A3, A3. So we have A3 goes to A3, A3, A2, A1. So we're replacing this A2 by the A2, A3, A3. And then we're replacing this A2 by A3, 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 A2, A1 prime, A1, and then we still have to have that little a. So we basically replace this, and now we have immediate left recursion. A3 goes to A3. We have this is the alpha 1, this is the alpha 2, and that would be a beta. Okay, so we have A3 goes to A, or A3 prime, and then we have A3 prime goes to A3, A2, A1, or A3, A2, A1, A3 prime. So that is that alpha 1. And then we do the alpha 2, which is A3, A2, A1 prime, A1, or the whole thing with the A3 prime follow. And then, of course, we need the... No, that's it. Okay, so we have A3 goes to beta, and beta A3 prime. And then the A3 prime goes to alpha 1 and alpha 2, and both alpha and alpha 1 followed by A3 prime, and alpha 2 and alpha 2 followed by A3 prime. So this is now the current set of the productions. So we have this, and we have that, and we have those. So that is for the elimination of immediate left recursion. And then you replace the A3s in here by this or that. So you get A2 goes to A3, or A3 prime A3. So this is now the A2. And then we do the A1, which means we're going to, this is where we're looking. So we have the A2, so we basically now get 4 A1 productions. We have, for that A2, we're replacing it by this. So this is A3, A2. So this is this, and then we replace this here, and then we replace the A2 by that. So this is little a, A3 prime, A3, A2. So that these two productions come from the first A1 production, and then we have the second A1 productions, which is A3, A2, A1 prime, as well as plugging this in A3 prime, A3, A2, A1 prime. So now we have A1 productions, all of which start with a terminal and then have variables following. A2 productions, all of which start with a terminal, then have variables. A3 productions, all of which start with a terminal and then have variables. And now we have to mess with the A3 prime productions. So there is our A3, so that gives us, we can plug this in. And we have another A3, we can plug that in. So I am sort of aborting this at this point. You basically get 2, 4, 6, 8 productions for the A3 primes by replacing the A3, this A3 by A, or by A3 prime. And the same thing for this A3, same thing for this A3, same thing for this A3. So this gives you 8 productions. Any questions?
I have a quick question about the step where we introduced A3 prime. I'm still not completely sure how A3 went to, and how now it goes to A or A3 prime.
This is where it comes from. You look at your immediate left recursion. You group them into 2 groups. The productions that start with that variable and the productions that don't. That gives you your alphas and your betas. And then you have the A, that variable A goes to beta 1 through beta n. So the stuff that doesn't start with A, and then you have that stuff that doesn't start with A followed by A prime. Okay, so this is where you have your A3 prime, because the beta was the little a here, and then you had two alphas, alpha 1 and alpha 2. A3, A2, A1 was alpha 1. A3, A2, A1 prime A1 was alpha 2. And so what you have here is, this is your alpha 1. This is your alpha 1 followed by A3 prime. So this is the prime variable. There we go. So alpha 1 and alpha 1 A prime, alpha 2 and alpha 2 A prime. Okay, and so that's what we have here. The alpha 1 is this, the alpha 1 followed by A3 prime is this, the alpha 2 is this, the alpha 2 followed by A3 prime is this.
I see the logic now.
Okay.
I wasn't seeing it.
This is tricky. You have to be careful in chasing all that, but there is some method to that madness. And so the important issue here is that now we have shown that any context-free grammar, any context-free grammar that doesn't generate epsilon. Of course, you remember we were talking about that. When we eliminate epsilon productions, we guarantee that there is no epsilon that can be produced by the grammar, so the resulting grammar. If you start with your original grammar G, oops, I don't want that. If you have your grammar G, then obviously the result is going to be, if you choose the original grammar, then once you've done all that elimination business, you will have a grammar that generates everything except epsilon, if epsilon was generated before. If it wasn't, then of course it is exactly the same thing. And so both Chomsky normal form and Greibach normal form obviously cannot generate epsilon. But that is not really an issue here, because we basically get that automatically once we eliminate all epsilon productions. And so what we now have then, we've shown that given any context-free grammar G, assuming it doesn't generate epsilon, we can replace that by a grammar, context-free grammar that is in Chomsky normal form, or we can alternatively replace it by a grammar that is in Greibach normal form. Chomsky normal form, of course, generates from a variable two variables or a single terminal. Greibach normal form generates something that always starts with a terminal and then has 0 or more variables following. Now, these are, of course, different. You have to make up your mind, do you want Chomsky normal form or do you want Greibach normal form? But either one of them is possible to achieve. No, not, of course, at the same time, because they're mutually exclusive.
Do you have any advice as to which one we might want to use? Are there particular situations where you kind of know where we would want to go in a direction?
Well, okay. You don't really want to use any of them because they tend to be messy. If you look at what you get in the example, for instance, here, we started with 1, 2, 3, 4 productions, and we ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 productions. It blows up. That's for Greibach normal form, and you've seen already for Chomsky normal form that things are not that much nicer. The deal here is not that you want to have something in Chomsky normal form. It's not that you want something in Greibach normal form. It is basically a theoretical tool. Chomsky normal form is going to be very useful for the purpose of coming up with a pumping lemma for context-free grammars, for context-free languages, meaning that we want to be able to show that certain languages are not context-free. And so what we have then is a pumping lemma, which we will deal with next time on Wednesday, which is predicated upon Chomsky normal form. So once you have a grammar, you can generate Chomsky normal form grammar for that language, and then the pumping lemma applies, and so that then you will see how that works. Now, Greibach normal form, on the other hand, has a different property. It has the property that it will always consume a single terminal. So, in other words, if you have a Greibach normal form derivation and you derive a word of length n, then that follows, if you have a Greibach normal form derivation, there are exactly n derivation steps, because in each step you're going to generate a terminal. And so if your word w, which of course by our convention is over the terminals only, then it follows that there are n terminals in w, and in each derivation step you're going to generate a single terminal. And so you need exactly n derivation steps in order to get that entire word of length n. That is of particular interest when we want to generate a type of automaton that accepts context-free languages. These are called push-down automata. And they are essentially finite automata with an additional storage device, a stack. We'll get to that probably after the exam. But for showing that a push-down automaton can always be constructed for a language that is generated by an arbitrary context-free grammar, well, we first construct a Greibach normal form grammar for that language. And then it is utterly trivial. I mean, it's embarrassingly trivial to construct a push-down automaton once you have things in Greibach normal form.
Excellent. Thank you very much for that.
Any other questions?
Professor, the fourth question in the assignment, the exercise said there are variables as a and b. Can we replace it with a1, a2, and a3?
Yeah, you can.
Okay, thank you.
I mean, as I said, the key issue is you have to fix some order. Any order will work. If you were to replace this by the opposite order, an and an minus 1 and so on and so forth, as long as you stick to it, any order will work. Okay?
Okay, thank you.
Any other questions?
Yes, Professor. I have questions about my exam, but maybe this can wait until everyone else has asked their questions.
Well, what is the question about the exam?
Well, namely, it's that, like, I was under the assumption from what you had said earlier in class that there would be partial credit offered for questions. and there was on question 3, I did the first 2 parts of each question, but I guess I just didn't read the last part where it said reduce the DFA, because I know that I knew how to do that at the exam time, but I must have just like skipped over that part when I was reading the question. So I didn't do that part, and so therefore I got 0 points for both, and that's over half my exam score. That is like about half my exam score.
Well, send me an email and I'll forward it. If you did something and it was correct, then you should have gotten partial credit.
Well, okay, maybe I don't know what if anything I did was correct or incorrect based on the feedback. I mean, the TAs were saying that like the answer is not correct, but they didn't specify if that was because I had forgotten the last step or because my initial steps weren't correct. And I don't know how the partial
Well,
credit is given out.
why don't you, if you've already contacted the TA, ask specifically what was wrong?
Okay, I'll do that.
Okay. Any other questions?
How do we contact TAs through Blackboard?
You can probably do that, but it's only in specific cases. If you say, I want more points, you have to talk to me. Basically, I'm shielding the TAs from unreasonable requests.
Well, in that case, like, I mean, I do think that I deserve more than 0 points on those questions.
Well, ask specifically whether this was wrong. What
Okay.
was wrong about that?
I emailed to elice@uh.edu.
You can do that, yes.
Okay, I already did. It's just that the TA's already replied via that. So I don't know if you saw the original email, but I did email you already about it. So
Well, if the TA says that, if the TA is specific about that this was wrong, then I'm afraid it was wrong.
well, okay, yeah, I'll try to get a specific answer from them.
Okay. Any other questions? All right. Well, then I will talk to you on Wednesday.
Thank you.
Have a good afternoon. Bye-bye. He